Hey everybody. Today we're talking about the normal distribution. Here we're in a situation where we have a continuous random variable with a density function that looks like a bell curve, like what I have pictured here. In a normal distribution, any value is theoretically possible, but outcomes closer to the mean are much more likely. Normal distributions are incredibly common in the real world. So, for instance, lengths of newborn babies have an approximately normal distribution, speeds of vehicles on an open stretch of highway, scores of students on a standardized test. All of these might have normal distributions. A normal distribution is always symmetric about the mean. In other words, its graph looks the same on the left and on the right. The probability of getting a result less than the mean is 50%, and the probability of getting a result greater than the mean is 50%. Normal distributions can be wide and shallow, or narrow and tall, or anywhere in between. And the difference is just the standard deviation, which is measuring the spread of the random variable. Equivalently, we can describe the spread with variance, which is just the square of the standard deviation. A bit of notation: we write n parenthesis mu comma sigma squared for the normal distribution that has mean mu and variance sigma squared, so standard deviation of sigma. By the way, the mean and standard deviation are completely determining the normal distribution. There's no other parameters necessary. The standard deviation of a normal distribution is visible on the graph. So we know the mean is at the middle, at the top of the bell curve. If you move one standard deviation in either direction, you get to one of the inflection points of the density curve. And by inflection point, I just mean the place where the graph changes from looking like the top of a hill to the bottom of a valley. An example: in a recent year, scores on the SAT were approximately normally distributed with mean 1060 and standard deviation 195. If X is the score of a randomly chosen student, then X has the normal distribution with mean 1060 and variance 195 squared. On this picture, I've labeled not just the mean, but also 4 additional points going 1 and 2 standard deviations in each direction. So adding and subtracting 195 to the mean 1 and 2 times respectively. The empirical rule is a simple rule for estimating normal probabilities. And it says that about 68% of values lie within 1 standard deviation of the mean, 95% of values, approximately, lie within 2 standard deviations of the mean, and approximately 99.7% of values lie within 3 standard deviations of the mean. So, in that SAT example, for instance, if we pick someone at random, there's approximately a 68% chance that their score is between 865 and 1255, 1 standard deviation below the mean and 1 standard deviation above the mean. And we can make similar statements for 2 standard deviations, 95% chance, and 3 standard deviations, 99.7% chance. To compute probabilities more generally and more specifically, we use the cumulative distribution function, or CDF, of X. Typically using technology, the CDF gives the probability that X is less than or equal to the value that you're interested in, which we'll call little x. So the picture is really worth keeping in mind. For a specific value, X, that I've labeled on the x-axis, the horizontal axis here, big F of X is going to be the area under this curve to the left of that X value. As I said, we typically compute this using technology. In R, the CDF is coded using the command pnorm, and you specify the X value you're interested in, then the mean, then the standard deviation. For instance, what's the probability that a random SAT taker scores less than 900, as pictured here? So I'm going to compute this using the cumulative distribution function, pnorm. I'm going to feed it the value I'm interested in, 900, want to get the probability less than 900. Then I feed it the mean and the standard deviation, 1060 and 195. I get 0.206, about 20.6%. Another example: what's the probability that a random SAT taker scores at least 1,000? So now I want a probability to the right, an area to the right. And the way I'm going to do this is by getting the probability to the left, the area to the left, using the CDF, and then I'm going to subtract that from 1, because the total area, the total probability under any density curve has to be 1. Basically, in a random experiment, something happens with probability 100%. So the area to the left, the probability to the left, is p norm of 1,000, 1060, 195. I subtract that from 1 to get the probability of a random result being greater than or equal to 1,000. I get 62.1%. One last example. What's the probability that a random SAT taker scores between 900 and 1,000? So the way I'm going to do this is I'm going to take the area to the left of 1,000 and subtract off the area to the left of 900. So p norm of 1,000, 1060, 195, that's the area to the left of 1,000, minus p norm of 900, 1060, 195. That's the area to the left of 900. Do a little bit of arithmetic, and we get 0.173, about 17.3%.